So welcome everybody to the third speaks seminar. Today, I'm happy to present our second contributed speaker, Manuel G. Algaba, who is currently working at IQ and quantum computers in Germany, and he's also a first-year PhD student at the Autonomous University of Madrid. Manu studied the degree of physics at the University of Córdoba, and there he developed a bachelor thesis on numerical simulation of plasma physics. However, he had very different interests, and finally he decided to move to Bilbao to study the Master in Quantum Science and Technology at the University of the Basque Country, where he studied the quantum simulation of lattice-gate theorem in his master thesis. After that, he got a job at IQ and Quantum Computers in Munich, and this is a quantum computing company that has that does different things. For example, it develops superconducting quantum computers, and it also studies different quantum computing paradigms, such as the most extended digital quantum computing, or the alternative known as digital analog quantum computing. After 1 year and a half working there, he has started his PhD at the Autonomous University of Madrid on the quantum simulation of the physics of many-body systems for concretely mixed devices. Today, he's here to talk about the area of quantum simulation, and more concretely NV centers or superconducting circuits, and his first works on this area, co-design quantum simulation algorithm of nanoscale NMR. So now we are ready, and the floor is yours, Manu. So start whenever you want.
Okay, thank you, Paula, for the introduction. So, good afternoon, everyone. As Paula said, I'm Manuel Algaba, and today I'm going to talk about this work that we developed in a paper that we published 2 months ago or so. It's called Simulating Nanoscale NMR Problems on a Co-Designed Quantum Computer. This is the paper, and we will cover some topics on the introduction for this paper, since I was asked to prepare a more pedagogical part. So first of all, we will talk about the hyperpolarization process. That is what we are going to simulate in our quantum computer. Then we will talk about generic quantum simulation, its main applications, and why this specific problem is better than usual problems in the realm of quantum simulation. And finally, I will talk about our paper, the co-design implementation of our algorithm. So first of all, the hyperpolarization process is a process that has its main applications are for imaging, both medical imaging and also molecular imaging, because in conventional medical imaging, for example, if you go for nuclear magnetic resonance, patients are injected with, 1 second, let's put the laser, yeah. So patients are injected with a contrast agent that reacts very strongly to some magnetic fields that you can create in this type of magnetic resonance machines. So when you put the patient here inside, you will be able to obtain a very neat image of the tissues of this patient. However, some of these contrast agents, such as gadolinium, they are not very nice, to be injected in people because they are not very biocompatible. So people said, okay, let's go, instead of using conventional contrast agents, let's go for nanodiamonds because they are very, very biocompatible. This is a piece of a nanodiamond. You can see here all the carbons, but the problem with nanodiamonds is that they are not very polarized at room temperature. And what you need for this thing to work is that you have a substance that can get very polarized when you apply a magnetic field at room temperature. So people started using an alternative in these nanodiamonds that is taking advantage of this naturally the defects that naturally appears on your nanodiamonds, such as the NV centers. that we can see here, since when you have a nitrogen appearing there in your nanodiamond and it only has 3 valence bonds, the remaining bond that here usually we would find a carbon. So this carbon cannot be here because there is no bond here to the nitrogen. So you create there a vacancy. And the point is that these MV centers, these nitrogen vacancy centers, they behave as spins effectively. So they can interact through dipole-dipole interactions with other spins in the surroundings. And then for doing this interaction, there is this process that is called hyperpolarization process that I will talk about a bit now. And the main point here is that you will be able to spread some magnetization from the MV center to the rest of the nanodiamond. And that is how you create the polarization that you want in these NMR experiments, for example. So this would be the physical system. We have an MV center here, and we also have some carbons around. But the MV center is not going to interact with all the carbon nuclei that are around, but only with those that are carbon-13 that are naturally appearing in your nanodiamond with a probability of 1.1%, because they have a odd number of nucleons. They will have a spin to interact with these on their nuclei. So they can also interact among themselves, and they are embedded in a magnetic field. But the point is, if we want to enhance this interaction, we have to embed the system, well, in a microwave driving field here. So now we would have all the Hamiltonian of this system. That would be something like the energy coming from the MV center, the energy coming from the nuclei, also from the interaction among nuclei, and the interaction amongst MV and nuclei. And of course, we have to add there this driving Hamiltonian term that we are using with this microwave radiation. This microwave radiation can appear in different ways. We can create it with different schemes. The easiest one would be the continuous driving scheme, in which you just send some kind of sinusoidal radiation there, and you can choose the phase, you can choose the frequency. So at the end, you enhance this interaction that we want to enhance, well, better or worse, depending on your parameters. But also there are other types of radiation we can send there. For example, this pulse driving scheme, in which we don't send a sinusoidal radiation, but just a very sudden and strong pulse. This has some advantages since it's resilient to some kinds of noise in the MV center system. And the point is, if we write down this Hamiltonian completely, this is going to look a little bit cumbersome, because you have all these terms for M centers and N nuclei. This will be a bit cumbersome, but we can study what is happening when we go to one MV center and one nucleus, and also doing some approximations and messaging along the way. So in this case, we have this omega c that would be the Larmor frequency, and this a that would be hyperfine vectors. And both of these vectors are depending just on the spatial coordinates of your problem. So this is something that is fixed as long as your spins are not moving in your problem. And also you have here these i's that would be the spin operators acting only on the nucleus. So this would be something like the Pauli operator, sigma x, sigma y, and sigma z, but acting on the nucleus. And also we have these spin operators acting on the MV centers, and we have labeled them as sigmas themselves. The sigma z is acting on the MV center, and this sigma x is acting on the MV center as well. So this would be like your natural Hamiltonian in your system, but this is coming from the radiation that you are sending there. So this is what you want to study at the end, how changing these parameters is going to affect the polarization of your system. The point is that for one MV center and one nucleus, you can find an analytical way for reaching the best possible polarization. So it's called this Harman-Hunt condition. It's just by taking the driving field frequency equal to the Larmor frequency, and this way you can, and with a bit of messaging as well, you can obtain this Hamiltonian that is not as ugly as before. But the good part here is that since these brackets are acting only on the MV center, you can see that if you plug in a plus state from the MV center, this plus state will automatically generate some kind of decreasing in the magnetization of your nucleus. So at the end, you are seeing that if you put a plus state, the natural Hamiltonian you're putting in this, you are studying with this system will create some magnetization in your nucleus. So this way we can use the driving field to spread the magnetization that is present in the MV center, in the plus state of the MV center. So how do we do this at the end in experiment? Well, the point is that you have to create first a plus state on the MV center, as we saw. This can be done experimentally, but by just sending some laser radiation to the MV center. And now that we have this kind of maximal magnetized state in the Pauli X axis, you know, then you can start sending this magnetization and spreading it around in the nanodiamond with the microwave radiation. So now that we have run out of magnetization in the MV center, we can keep doing this. We will reset the MV center again with a laser, and then we keep doing this until we reach the desired polarization. So this way you can highly polarize an MV center by using this hyperpolarization process. You can see here how this would look like in a graphic. This is for 2 nuclei and 1 MV center. The green and the red ones are the magnetization or the polarization of the nuclei. And you see this, this is after applying the hyperpolarization process once, with one cycle, only one reset for the MV center. If we studied this without hyperpolarization, this would look like a zero line, because what you have there in the nuclei, since they are at room temperature, you will have some kind of fully mixed state. So at the end of the day, it will be very nicely approximated by an ensemble in which half of the times, 50% of them, you have a state 0, and the other half of the times you will have a state 1. So at the end, this would have a magnetization 0 in the z-axis. The point is, since we are hyperpolarizing this to create this magnetization, the MV center is also losing its X magnetization. This is the X magnetization of the MV center. And we can see here that this depends, the magnetization that is transferred, on the different frequencies that we can use for this driving field. So the idea is to find the frequency that makes the highest polarization for your sample. So for doing that, also you can repeat this process several times, as I said before. So if you see here, the first cycle would be less polarized, the second more, and so on, until you can reach some kind of saturation. Indeed, you can study the saturation in terms of these cycles, and you see that for the proper parameters of your time, like the frequency and also the time for which you are applying this microwave radiation, then you can, for these proper parameters, you can find a saturation curve. So this was very nice, but this was just the problem we want to simulate on our quantum computer. And for simulating it, we will see a brief introduction to quantum simulation techniques, because usually in quantum simulation, what you want is to map just a very, very big Hilbert space problem to the Hilbert space of your quantum computer, so you can efficiently simulate it. So the most studied techniques, well, problems on quantum simulation, I would say it's the ground state problem, in which you just find the ground state wave function and also its energy for a given Hamiltonian. But we will be focusing more on the quantum dynamics problem that is also very studied, in which you know very well this initial state of your quantum system, as we do, and then you just want to know what is going to happen after some time of the evolution of your Hamiltonian, as it's happening with our previous problem that I showed you before. So as probably some of you already know, the most used technique here is structuralization. So if you have a Hamiltonian composed of L terms, you will decompose them in such a way that you can simulate them easily on a quantum computer. If we start with two terms, since they are not commuting generally, because if they commute, you apply just one evolution operator and then the evolution operator according to the second operator, and that's enough. But since they are not generally commuting, you have to split this into smaller steps. So you divide the time by the number of steps you are implementing, and then you just do like very, very small evolutions. First the first operator, then the second operator, and you keep doing this until you reach the desired precision. Of course, the error is going to look something like this. And if you go for more terms, you can find this equivalent formula. The circuit here would look something like this, in which first you implement the evolution operator according to this 1 and 2 qubits, then the 2 and n, then the 1 and n, and you keep going until you do all the interactions, and then you repeat this step for the remaining s minus 1 times steps. So the error here is going to be proportional to this thing. Of course, you see here that this is proportional to the sum of the coefficients. Well, this is the coefficients of the Hamiltonian you are putting here. So you can find a bound if you just think the worst case, in which you have the sum of all these terms being one of them being the maximum and all of them, of course, being equal. So all of them are the maximum coefficient terms. This would be this lambda. And since you have L terms, at the end, this bound would be L times lambda times T divided by S. So the good point is that there are some techniques that can improve this that are very interesting. For example, these randomized structuralization processes, also this Q-drift by Errol Campbell. And in these techniques, you just randomize your process. You take first wherever H2, then H4, then H5, and this way you can obtain less errors than doing usual Trotter. But to be honest, this is the easiest way, and at the end, for showcasing some things, it's okay to use it. But also you can find some variational approaches that are also very interesting, but we will not focus on them in this talk. So the main applications of these quantum simulation techniques is, of course, for quantum chemistry and condensed matter. So one of the most prominent is the electronic structure problem. I'm sure you have seen this before, this kind of Hamiltonian in electronic problems, where you decouple your nuclei degrees of freedom from the electronic ones, and then you just have this Hamiltonian. So you can also simulate this using this kind of first quantization, in which you have a more an uglier Hamiltonian, but it's more common to find in quantum algorithms the second quantization version, in which you just take this and massage it a bit until you find something like this, where the A dagger is the creation operator for fermions and the A is the annihilation operator. So this way you can represent a very broad group of Hamiltonians that are used in quantum chemistry. However, these constants are looking a bit nasty, but okay, it's something we can cope with. But the good point is this is also representing some very interesting problems in condensed matter, because if you fix some of these constants and the relations between the A's and so on, then you can find something like the Fermi-Hubbard model that is very used in condensed matter physics. It's a kind of a toy model that is showing lots of interesting behaviors, but still it's not fully understood for higher dimensions, because for one is more or less understood and solved. But the point here is that you will have to use these fermionic and annihilation and creation operators, and And you cannot find this easily on a quantum computer, because on a quantum computer, you will usually have something like Pauli matrices and CNOTs and things like that. So you have to use this kind of famous fermion to qubit mappings, such as the Jordan-Wigner transformation, in which you just map the statistics of your fermions or the anti-commutation relations that these operators have to the operators you have in your quantum computer. And this way you can simulate fermionic systems. But the problem with this is that you are going to find a nasty number of gates that you have to implement with a nasty depth that you will not be able to simulate on current NIST devices or on foreseeable future devices, close future devices. So the good point about the problem I'm going to show you after this, well, this that I showed you already, this hyperpolarization process, is that since the spins are especially well defined, and you don't have this kind of undistinguishability you have in fermionic problems, you don't need to use this kind of fermionic operators. So the good point is you don't have at the end these so many gates, and is more suitable for NIST devices, because indeed, if we take a look on the number of gates that you need, from work, and you see for ethane you can simulate it with 60 qubits, and for the deterministic version of Trotter you need like 10 to the 25 gates, what is horrible. It's something really, it's the nightmare for a person working on quantum computing probably. So this is the bad part of quantum simulation, but we are focusing on our problem, and we will apply this kind of co-design concept. This co-design concept is just if we have a problem, we want to make the most of this problem by choosing a tailored software and also a tailored hardware for this problem. So for example, in chemistry approaches, you need lots of gates if you want to totalize, but if you do variational algorithms such as VQE or VQS, you may need less gates, because it's something that is optimized each step. So at the end, the number of gates are usually not that many. But the problem is if you want to go for VQE, then you need to have a very fast feedback loop from the quantum computer with the classical computer. So you also need a kind of tailored hardware. So this would be this kind of combination. I've explained this co-design space for the problem in chemistry. Just a random example. But in our case, we will apply this spirit as well. So first of all, we are going to focus on two models for this hyperpolarization process I showed you before. First of them is, as I explained before, is this MV center interacting with the carbon embedded in the microwave field. But we are going to neglect first the interactions among nuclei, because these interactions are like 3 orders of magnitude less than the interaction between MV centers and carbon nuclei. So we will just neglect them to start with this and to see the easy example. But we also considered the interacting case just to see how much neglecting this will affect. And indeed, this would be something like an all-to-all interaction problem, while this is more kind of a central spin problem. So now, the Hamiltonian can be split, as I said, with Trotter. We are going to split with a single qubit gate part and then the 2 qubit gate part. The single qubit gate is very easy to implement. There are not very nasty things, not many nasty things that you have to do. While the 2 qubit gate part is going to be a bit more challenging. This would be our Hamiltonian just for the non-interacting case for NV centers and N nuclei. Once we have expressed this in qubit operators, so it's easy to see these X and Z's. So these A's would be constants of the problem, and this X is going to be acting on a qubit that represents the nuclei, while this Z will be acting on a qubit that is representing the MB center. So to simulate this at the end of the day, we will need to adapt it to our native gate set in this kind of co-design spirit, because we want to make the most of each part that we can. So we want to do this as efficient as possible. So we just took our native gate set to simulate very efficiently this, instead of going, for example, for this kind of compilers. And I think this is more or less generic in superconducting qubits, that you can find this kind of single qubit gates. One is a parameterized rotation along some axis in the XY plane, and this one is a rotation along the Z axis. But the good point about this second one is that it's a virtual one. You can do it without really implementing it in your computer, because even though this does not commute with the rest of gates you have, you can find a kind of a commutation rule in which if you have first RZ and then RXY, then you can switch them by just adding some phase to these RXY, as I think it was IBM did a couple of years ago in a paper. So if you use this, all the RZs, or most of them, will be free for you in your quantum computer, and this is nice. Now also the 2-qubit gate that we will be using is a controlled set, but the point is that since this controlled set is equivalent up to some RZ rotations to this UZ set that is just an exponential of a set two-body term, then we will just be using this our native gate set, because it will make everything more clear, I would say. And also the only thing you are including for going from here to here is a virtual set rotation, so it's not something that really matters. So if we see now the circuit of the algorithm itself, it may seem a bit lengthy, but not so much. We focus first on the evolution of the microwave driving field and the Hamiltonian itself. We see that for a single Trotter step, we can do first all the single qubit gates and the driving simulation. Then we go for the ZX terms, that would be these ones, then the ZY, and then the ZZ. This ZZ can be implemented natively with the gates I showed you, as I said, because it's just exponential of this ZZ and it's parameterized. But these ones you need to rotate in order to obtain this XZ and this YZ. You need to rotate the nuclei that you have here, because we are taking one in the center and 2 nuclei for this example. And the point is, each of these single Trotter steps will be in this Trotterized evolution, so you will perform this many times. So before, if you go for the initial state preparation, you will prepare the MB center, as we said, in the plus state, so this hyperpolarization can occur. If it were not a continuous driving, but a pulse driving, then the initial state would change probably. But we are just explaining here the continuous driving, even though we also implemented the pulsed driving. So here, for simulating the thermal state, we used on the nuclei this kind of random X Paulis that are going to switch your initial state from 0 to 1 randomly. This is more or less a technique that we implemented from Cilio et al. And the good point is that this is not going to create a lot of overhead in the measurements you need to do. So you just change this random X from one run to the next run in your quantum computer, and that's enough for simulating your initial fully mixed state. So now you do the Trotterized evolution, and you have to reset, as we did with the laser, the MB center again. So here we have to reset it in our quantum computer, and this is not that easy. Why? Because it's a non-unitary quantum operation, and most of the operations you see on quantum computers, they are at the end of we try to make them unitary. So what we did here is just to use this quantum circuit refrigerator, this QCR, that allows you to cool a qubit to the ground state. So this is used, for example, for resetting the state of the qubits from one run to the next one. But here we are using it for mimicking. We are using a non-unitary quantum operation in our quantum computer for mimicking the non-unitary quantum dynamics that we find in our problem. And I think that's nice because this is not so often, I would say, in occurring in superconducting chips simulations. So now you create also the blast state in the MV center, you evolve again, and you keep doing this for the number of cycles that you want to simulate. At the end, you only have to measure, as we saw, the Z Pauli for the nuclei and the X for the MV center. So now we know all the magnetization after some time evolution that we performed in this simulation. If we want to simulate also the interacting case, it's very easy. At the end, you only have to add some missing gates here. For example, the one connecting 1 and 2, and it would look something like this, but with an extra 1, even though a bit different, but not very important. So now the problem is, this is very nice, but how do we simulate this on a quantum computer, really, if we go to the hardware and we go to the topologies? Usually, there are some kind of non-very trivial topologies in superconducting quantum computers, but there are also some that are like the square grid that we are using just to showcase this. And if we want to simulate, for example, the non-interacting problem on the square grid, first of all, you will need to solve the swap routing problem. What is this? The swap routing problem is if you have a qubit here and you need to make it interact with this qubit, of course, you need to swap this one here, and now you can make them interact. But this is easy when you have two qubits and one interaction. If you have a lot of qubits with lots of interactions, then how do you optimize the depth and the number of gates so you can still do this computation on your quantum computer? So there are lots of different techniques, but most of them are, I would say all of them are not analytical. They are kind of numerical, of non-deterministic, so they don't give always the best result. This is for our problem in the square grid, the number of swap gates that you need to implement to simulate one further step versus the number of qubits that you have here. So you see, this is scaling more or less okay, but we want to benchmark this square grid, this very conventional topology, against the co-design chip that we created or proposed, this that I will show you later. So we want to make the most of this square grid before we go to the co-design case. So we said, okay, let's try to forget about these numerical techniques because they are good, but they are giving you some problems sometimes. And let's try to come up with an idea doing an analytical way, solving this. And indeed, we said, okay, let's forget about the square grid. Let's think what we have is just this line there. So we linearized the square grid. And we imagined we don't have a square grid at all. We just remove the connections that are not in this line. And now we can perform here the simulation. And indeed, it seems like a very simplistic and stupid idea, but it will work better than the numerical approaches for this problem. So we just focus on a piece of this line and we label the qubits. The 0 will be the MV center. Now we perform the neighboring interactions. We swap around with the following qubit. We perform the next interaction. We swap around and we keep doing this along all the line. So this way, we will find the one further step simulation in a linear number of swaps in a linear depth. And if we plot this here compared to the numerical approaches, we see that we outperform the numerical approaches for this case. So we said, okay, this is the best we can do on the square grid, even though it's just taking a line on the square grid, what is almost absurd, but it's better than just taking the numerical approaches. And Now we said, okay, now we are good to compare this against a more co-design approach. So we said, let's try to resemble this structure on our chip. This is kind of a central spin problem. So just place one central qubit and surround it by all the qubits representing the nuclei. The central one will be representing the MB center. So this way we can do all the interactions here, and we need indeed 0 swaps. So everything works smooth. The depth is still linear, so we have not worsened the depth. So this is very nice. We found a chip that can allow you to implement the same simulation with less swaps. But we said, okay, even though this interacting problem was not meant to be done on the chip, let's try it again with the co-design chip. So let's compare first what is happening on the square grid. So we see for this, we would require to do all the interactions between neighboring qubits. Then we can swap the odd qubits with the ones on the right. And now we can do again the interactions with the neighboring qubits and swap around the even qubits with the ones on the right. So this is called the odd even sorting. And if we keep doing this, we will find a simulation in a linear depth, so linear number of steps, but in a quadratic number of swaps. And if we try to do this on the start chip, we will see that we can do all the interactions. Now we swap first nucleus, we do the remaining interactions, and we keep doing this until we find the desired simulation. This will be now in a quadratic depth, but with a linear number of swaps. So we have decreased the number of swaps, but there is a price to pay in the depth. So if we take a look now on the percentage of saved swaps, we can see that for the non-interacting case, we are saving up to 100% of the swaps, of course, but still for the interacting case, we can save up to 90% of the swaps with 20 qubits, and this keeps growing asymptotically, so it's nice, even though you are paying the depth price. So how do I take this to a hardware problem? Because, okay, if you see this and you know something about superconducting chips, you will say, how the hell I'm going to connect more than, I don't know, 8, 9, 10 qubits to a central qubit, because this is impossible, because the capacitance will change, then you will not be in your qubit regime anymore. And so we said, okay, let's change the central qubit by a central instead. So this is the central resonator connected through tunable couplers to the qubits in the edges. And this way we have plenty of space for connecting qubits, and this will create no more problems. This is scalable to several tens of qubits, and we can connect here the QCR to the resonator just to reset the MB center qubit as we saw. But how this would work? Well, you just pick up a qubit, and we are going to call this qubit as central qubit. So you swap the central, well, you create the state that you want on your qubit, and then you swap it to the resonator. Now you make it interact with the rest of the qubits, and once you are done and you want to measure, you put it back in its place. You could say, okay, this seems very nice, but still this could have some problems, because if you want to do some gates with the resonator, you will have to drive the resonator. This will populate all your higher states, and then this will be kind of problematic. But the point is, for doing this control set and these iswaps, we will not need to drive the resonator, but we can just drive the coupler, and then we are good to go. So this is something you can do. Indeed, we simulated the fidelities of these gates, and we found that you can do iswaps and control sets in this resonator qubit structure with 0.99 fidelities. So it's kind of state-of-the-art fidelities. It's not something great, but it's something okay. So what are the results? At the end, these solid lines are the results you would obtain ideally if you would have no noise, but the problem is that you have noise in your quantum computers. So the dotted lines are when you include noise. You see if we study one of these peaks, of course, each of these peaks is going to be for one nucleus that will create a resonance. And if we study one of these peaks, we see this is the ideal one and this is the noisy one. So we want to estimate this, but we will obtain this. So we want to see if we are really making a big mistake by including the noise of your quantum computer. So first of all, we will take one benchmarking function that is this psi rate, in which we divide the height by the sigma. The sigma is the width of the peak and the h is the height. Why do we do this? And we average, of course, over all the nuclei. We do this because the noise is going to flatten and also shift a bit your peaks. So the highest this psi rate, the closest it will be to the ideal case. So you can compare if it's affecting more your noise to your simulation or not with this psi rate. But also the second benchmarking function will be this relative error of the omega ideal versus the omega noisy. This is how much are we misplacing omega ideal by choosing omega noisy indeed, because this is what we are doing with the experiment. So this would be the relative peak frequency error. If we study this in our simulations, we can see that for the psi rate, for a broad range of 2-qubit gate errors, if this is the ideal one, co-design one is going to approach the ideal one way faster than the square grid. And if we go for the peak frequency error, we see that also the square grid will be worse than the co-design that is approaching faster the ideal case. And indeed, you can see here that if you want to obtain this, for example, this accuracy or this error, with the square grid, you will need 10 to the -4 in the error of your 2-qubit gates. But with co-design, the same error will be just with 10 to the -2. So you are saving up to 2 orders of magnitude on the errors of your 2-qubit gates just by picking a very specific solution for your problem. For the state-of-the-art case, you can just improve the results by a factor of 3 roughly. So this is still very nice. So at the end, just to conclude, I will say that nanoscale NMR is a problem that has a highly suitable structure for simulation on quantum computers. Also, the hardware on which the simulation algorithm is implemented really matters because you can save lots of gates with it. Also, custom co-design hardware concepts can be developed to fit the problem, as we did with the creation of this specific structure, the reset with the QCRs, and the resonator placing in the middle. And finally, that co-design is a promising approach for niche devices, since it allows you to save lots of gates if you apply it instead of more conventional approaches. So thank you, everyone. And if you have any question, I'd be delighted to answer.
Okay. Thank you, Manu, for your nice talk. It has been very interesting. And now, if anybody has a question, he or she can try to unmute and ask the question, or just write it on the chat and I will read it out loud. Okay. So maybe as the questions come, I can ask one myself, because I have many. I think it's been very interesting. As I understood it, what you have done is to simulate these. So these are noisy simulations of the real computer.
No, it's not the real. Yeah.
Or have you done it? So your code has been run using a noisy simulator.
Yeah.
And do you think it could be applied on a real device, or have you planned on doing that?
Yeah, we have some plans. We have to see still because, you know, maybe you find problems for implementing this on a quantum computer, but still there are some more tricks to apply before you go to the quantum computer, like noise mitigation and so on, that may allow you to go a bit farther and push it a bit. Yeah.
Okay. I also thought that you said that structuralization is one, if not the main technique in quantum simulation. But as you said, nowadays actually there is a big hype in these quantum machine learning techniques, such as these variational quantum algorithms. Why did you disregard the use of these algorithms for this work? Instead of this structuralization?
No, of course, you can use plenty of different algorithms for quantum simulation. There is a complete huge slew of algorithms. Yeah, but we just picked this up because it's the most used one in the community. So we said, okay, let's try to showcase co-design with the most used algorithm, because at the end is what people are going to understand easier. Yeah. Yeah, but that's a nice question, because maybe we should also try to push it a bit to include other algorithms. We tried to do that a bit on the paper with this QDIF algorithm, but we didn't implement it at the end. Yeah, but yeah.
So, okay. Well, I don't see any questions. If someone wants to ask something, just you can write on the chat. If not, I think I will ask like one last question myself. Maybe I have one like regarding the results of the peaks of the frequencies. Maybe you can go to that slide.
Yeah.
Yeah, because when you have this, in this case, you have one MV center and two nucleus.
Okay.
Yeah, so you have two different frequencies for each nucleus. So in reality, when you want to find the frequency, how do you do that? You need to use different frequencies to hyperpolarize each nucleus.
Yeah, that's the point. When you go to the experiment, how do you find the optimal, frequency for this? Well, first of all, this is kind of a toy model, so it may be not that difficult to find this experimentally, even though it's kind of challenging sometimes to find some parameters that here in your quantum simulation you can just extract from the quantum simulation. And experimentally, not all of the parameters are accessible. But here you have, of course, two peaks. And the question is, where do I get not the maximum polarization for this nucleus, but the maximum polarization in total? So the sum of all of them, for example, this could be one question. Yeah. So this is the idea that you will not know in general. So indeed, something that I didn't show here is that we created a randomized, randomized scenario generator in which you have all the random possibilities of having here the nucleus, here the MB. So at the end, you have an average on what could work for more or less everything. So this is a very good point. Yeah. It's something I didn't address here because it was out of the scope of this talk. But yeah, we had to do it. Yeah.
Well, I have a question here in the chat. Mikel Garcia asked if you have considered more topologies that could be more efficient for the interacting case.
No, we have not, but indeed the problem with the interacting case is that it's an all-to-all problem. So you would require, if you want to do this without any swap, like a all-to-all connected quantum computer. And even though this is very interesting, theoretically, it's very difficult to do in experiments. So we have not gone for considering more interesting topologies for the interacting case more than this thing. Yeah.
Okay, so if no one has more questions, I think that we could end this here. And thank you so much again for your talk. I really find very interesting this kind of medical applications of quantum simulation. I think it has been really easy to understand. So congratulations and thank you.
Thank you, Paula.